In this lecture, we will discuss chapter 5. In this chapter, we discuss exponential series for complex quantities, circular functions for complex angles, and hyperbolic functions. So that means we already discussed in our lower classes that e raised to how to represent e raised to x, cos x, sin x, etc. for all values of real numbers. Using all the properties, we will find expressions for e raised to x for x as complex numbers. Similarly, cos x if x is complex number, sin x if x is complex number. So in today's lecture, we will discuss the exponential function and circular functions. So if when x is real, if x is real, we have e raised to x equal to 1 plus x plus x square by 2 factorial plus x cube by 3 factorial plus etc. Using this result, we will find an expression for e raised to x when x is a complex number. At present, this has no meaning if x is complex. Okay, so we let x be a complex number. X equal to a plus I times b, or you can write it as r times cos theta plus I sin theta. Then what happens when this value, this x is replaced by this quantity? So we will find an expression e raised to x by replacing this x by this one. Clear? Then you will get that as 1 plus r times cos theta plus I times sin theta plus r square times cos 2 theta plus I times sin 2 theta plus here we have divided by factorial 2 plus etc. This is because cos theta plus I sin theta whole raised to 2 is cos 2 theta plus I sin 2 theta, okay, for real values. So this theta, since this theta is real, we can write whole square of this quantity as cos 2 theta plus I sin 2 theta and so on. So this can be simplified as this is equal to 1 plus r cos theta. I collect all the real part first, plus r square cos 2 theta by factorial 2 plus next we have r cube cos 3 theta by factorial 3 plus etc. plus now you collect all the terms with I, so I can be taken out, then the remaining terms will be uh, sin theta r sin theta plus r square sin 2 theta by 2 factorial plus etc. So this will be the remaining term. We know that this r and theta are real numbers. So if you consider this series, you can say that this series is dominated by a series, or we can write it as less than or equal r plus r square by 2 factorial plus etc. Because modulus of cos theta is always less than or equal to 1, or this cos theta can be replaced by 1, so you will get this inequality. But we know that this is convergent because this is r, because r is, sorry, this is equal to e raised to r, and this r is real number. For every real number we define e raised to r, that's a finite quantity, so we can define this as a finite quantity. That means this equation makes sense because this is a real number plus I times this is a real number. So this can be considered as a complex number. So if you replace this x in this equation, if you replace this x by any complex value, you can get e raised to that complex value as and again a complex number defined by this equation. Okay. Now onwards we can define e raised to x for every x for real value or complex values. So now here note. So for any real or complex, we write e raised x equal to 1 plus x square by factorial 2 plus x cube by factorial 3 plus etc. So now we have defined e raised x for any complex number x. So one remark is this e raised x satisfies the same law of index. So e raised to x satisfies for real or complex. E raised to x plus y is equal to e raised to x into e raised to y. Now, if we put x equal to I theta, where theta is real number, we have e raised to x equal to 1 plus x square by 2 factorial plus etc. implies uh, e raised to I theta equal to now this is a complex number. This makes sense. You already seen that what does this expression stands for. This will be 1 plus I theta plus I theta whole square by 2 factorial plus I theta whole cube by 3 factorial plus etc. So when you separate the real and imaginary parts, you will get 1 plus, from this you will get a real number. That is I theta whole square divided by factorial 2. So that will be minus theta square by 2 factorial. Then you will get real number from the next term after this power 3. So that will be theta raised to 4 by factorial 4 minus etc. Uh, then we need to collect the imaginary part, that is I times. From the first you can get theta, from this minus theta cube by factorial 3 plus theta raised to 5 by 5 factorial minus etc. So these are the real and imaginary parts of e raised to I theta. So that can be written as cos theta plus I times sine theta, because we know that what is cos theta for a real value theta and what is sine theta for real value theta. So for real numbers this is defined, this is the cos theta and this is sine theta. So e raised to I theta, for this complex number e raised to I theta gives cos theta plus I sine theta. Then e raised to minus I theta gives cos theta minus I sine theta. Then from these two equations you can get cos theta is equal to e raised to I theta plus e raised to minus I theta divided by 2, and sine theta as sine theta equal to, that means this equation e raised to x equal to 1 plus x square plus x square by 2 factorial plus etc. for complex value x is consistent with whatever we have discussed in the lower classes. Okay, so that this equation enable us to remember those equations. Now, using this motivation, we can define the circular functions of complex angles. Okay. So for that, consider, we know that for a real value, for a real x, we know that sine x is equal to x minus x cube by factorial 3 plus x raised to 5 by factorial 5 plus etc. and cos x as 1 plus, sorry, 1 minus x square by 2 factorial plus x raised to 4 factorial minus etc. So now we need to find out what is sin x and cos x for complex values. So we define cos x equal to 1 minus x square by 2 factorial plus x raised to 4 by factorial 4 minus etc. for all x belongs to complex number C. Yeah. Similarly, sin x. We define sin x the same manner. X minus x cube by factorial 3 plus x raised to 5 by factorial 5 minus etc. for all complex numbers C. Complex number means if you take a complex number x, then find out the series. Okay, this series gives a finite complex number again. Then define that complex number. Define that complex number as cos of that complex number. Similarly, we will define sine of a complex number. Sine of a complex number is defined by choose that complex number first, then evaluate the series. Find the infinite sum of this series using that complex number. Then define that complex number as sine of that complex number. Okay, this is the idea of defining sine and cosine of complex values. Clear? So we start with this definition. Then we will prove that this cos x and sin x satisfies the same properties of cos x and sin x when x is real. So from this equation, you can get what is cos x plus I sin x. You can evaluate that expression from these if the whatever be this x, real or complex. For the time being, I write cos z and sin z for cos x and sin x in order to identify these angles are complex. So by definition, what is cos z? Cos z gives cos z equal to 1 minus z square by 2 factorial plus z raised to 4 by factorial 4 minus etc. and sin z. Sin z equal to z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus etc. So when you evaluate this cos z plus I sin z for a complex number z, still you have the sum of these two. Okay, so that is 1 minus z square by 2 factorial plus z raised to 4 by 4 factorial minus etc. times uh, sorry plus I times the other series z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus etc. So this can be written as this is equal to 1 first collect 1 from this and iz from this. Okay, so that will give plus iz. Then you collect this term, that is minus z square by 2i, that can be written as iz whole square by factorial 2. Okay, then collect this term, that will be plus iz whole cube by factorial 3 plus this is nothing but e raised to z. Okay, we already discussed what is e raised to z for a complex number is it. Okay, so this will give e raised to z. That means if even if this z is a complex number, you can get the equation e raised to z is equal to cos z plus I sin z. Okay, we already seen this equation for real values of x. Okay, so this is also true for complex values. That is what we have to establish here. E raised to z can be written as cos z plus I sin z for all z belongs to C. For any complex number z, we have sin z equal to z minus z cube by factorial 3 plus z 5 by 5 factorial minus etc. Cos z equal to 1 minus z square by 2 factorial plus z raised to 4 by 4 factorial minus etc. So cos z plus I sin z equal to 1 plus iz plus iz whole square divided by 2 factorial plus etc. So this is equal to e raised to iz. So this was that for all complex number z, e raised to iz equal to cos z plus I sin z. So from this you can write cos z minus I sin z equal to e raised to minus I z. So using these two formulas, you can write cos z as e raised to iz plus e raised to minus iz divided by 2 and sin z equal to e raised to iz minus e raised to minus iz divided by 2i for all z belongs to C. These formulas are called for Euler's exponential values. So using these formulas, you can find the identities. Sine, we know that sine x plus y is equal to sine x cos y plus sine y cos x. So you can prove this identity for all values of complex number as well. If this is true for all real, we can say that this is also true for all complex numbers. Okay. So using these identities, you can prove, or these Euler's exponential values, you can prove all the real identities are to be true for complex values.